So we'll start with learning statistics for data science. Again, we are trying to cover the concepts of statistics and how it is used in data science. So it's very important to understand typical data science life cycle. Mm, Before I go here, I want to talk a little about data science and machine learning. Maybe different people have different opinion about data science and machine learning. Are they both same or are they both different? How do they fit together in a project? So I will share my understanding, what I have learned from different research articles. See, there exists something called software projects. People in industry, they keep doing lot of software projects. So assume there is a project with a company ABC, project P1. This project is about maybe about SBI, that online SBI, whatever software we have on banking, SBI banking software. So you use different applications about SBI banking. You use Yono app sometimes. If you are SBI customer, you might be knowing this. You use internet banking, or you may be using some personal banking. Lot of features exist. So this project P1 from this company ABC is about designing a software system for this SBI bank for doing the banking transactions. So you can, individual can log in using internet banking, do transactions, send money, all those functionality. Assigning ATM cards, credit card, debit card, changing pin, lot of stuff. It's a very big project. In this big project, at some point they wanted to do some analysis, because since machine learning and data science is new and trending now, they want to use this machine learning and data science. So see this as a software project. This P1 is a software project. In this project, they wanted to take advantage, they want to do some predictions. We know machine learning can be used for doing predictions, classifications, right? So they have the customer data, they have the real time data with them. Okay, so we all are customers of this SBI bank, assume. So they have all our data, how many cards we are using, how many transactions we do, right? So this SBI maintains complete information, so they have a real time data with them. Now they want to leverage or take advantage of these concepts of machine learning and data science, do some predictions, recommend some credit cards. You do some transaction, immediately they give you some recommendations, right? So that and all they want to do it using machine learning. Or if they know your previous transactions, then they will be able to identify that future you are going to make some transaction, so they'll give some alerts to you. Maybe you want to purchase something, go for a holiday. So lot of things they are doing based on our transactions which they are having with them. So that is, so this ML or data science is just a small part of this big project P1. Okay, because it is not a simple one. It has lot of database storage. It has lot of web modules. They have to build applications, mobile app, right? So lot of things are involved in this huge project. In that huge project, this part of machine learning and data science is just a small step in between somewhere. It's a small module, right? So don't see this ML as a separate project. Maybe we have some pure ML projects which only the things which all researchers are doing today, taking some data set, applying some algorithm, trying to find some result, and using that recommendation for solving some uh, human problems, right? But industries, if they want to use in certain banking projects like this, they can include these concepts, machine learning and data science, to make their business more effective. Okay, so it's just a small step in that big project of banking. Now, again, in this small module, we were talking about data. We know always that for machine learning, data is the heart of it. So when you have this data, you have to do lot of data pre-processing. You have to do a lot of data pre-processing. Why? Because the data should be very no well structured, or it should be clean, in the sense there should not be any junk values, right? Data should be very accurate, so that on that data, when I form a ML model, that should be it should give me better accuracy. So we have to do lot of operations with the data. We have to clean data, we have to know visualize the data. So lot of data pre-processing is involved before you go and apply your ML algorithms, or you build a ML model on that data set. So when you have a data with you, here comes the picture of data science. Once this is step is done, then you go for ML model building. So I hope you understand where this falls. So when you have the data with you do a lot of data pre-processing, cleansing of data, trying to derive insights from this data. Right. Maybe you want to form a model, you can go for ML model, but if you want to make some insights, you want to identify some patterns in the data, you can do it using data science. So in that huge project, if they want to make some insights, same SBI banking, that SBI people want to make some insights, draw some patterns, identify, like I am a customer, they want to identify what is my monthly transaction in online shopping, how much I'm doing, or maybe for traveling, booking train tickets or flight tickets, how much I'm spending. So they want to do some analysis and give me some offers, so that I use their credit card, or you do there some transactions through their online banking. So they want to do derive some patterns, identify relationships among the data set, or derive some patterns, produce some insights with that, which can be useful for their business. So that and all is done using this data science. So when you have a data with you, maybe I can do only a data science part and do my business, because I want to draw some insights. I can draw it here. Or you want to build some prediction model, then you can go for machine learning. Okay, so this is the flow. Generally, it happens. I hope it is clear how these two are linked to each other. Sometimes in a project, you can have only data science, or sometimes you need only machine learning, or sometimes you use both data science first, then you go for ML. So we have different jobs for each of these particular skills. So in that, we will first study, given a data, how we apply these techniques, or maybe one technique is statistics, how we use these statistical techniques in data science. So this is the data science life cycle I'm talking about. Maybe this is same for even for machine learning in some cases. So understanding the problem, then preparing the data, exploratory data analysis, modeling the data. Here comes your ML, then evaluating the model and deploying the model. So from this, I would say only no these three majorly uses statistics. Okay, so when you are preparing data, you want to understand the business problem, or you want to do EDA, we use statistical techniques to do that. And we can use statistics at this point to, if there are multiple models, you have designed M1, M2, M3, multiple models are there, which model to choose? Okay, among these three ML models, which one to choose? In that step also we can use statistics. So that's only one step here, but most of the thing we use statistics in this EDA or data cleansing, right? In these two steps, we need this statistical techniques. And you can also see, this is one typical life cycle of data science or machine learning. But like I said, there are three ways. I can have one purely for data science for deriving some insights, purely for machine learning, three for both combined. So this case, if you take purely on data science, right? So we are going to see how statistics is used in this case, where I have given a data set, and I have to derive, identify some patterns with that data, see about no, like if it's a banking example, understand the money spending of the customer, how he is spending his monthly expend money, what he's earning. You identify some patterns. Based on that, you can derive some insights, make some business decisions. So at a higher level, data science, I would say, statistics can be used to derive some insights from the data for making effective business. So this is how it is used. See, during data cleansing, you need to identify the outlier. We will maybe we'll talk about this outlier detection. So when you have data set with you, if I plot it like this, something the full data is here. Or if I plot the data points, every data point is here, but there are few data points here and there. So these are outliers because they are not at one place. So these things can be considered outlier. So there also we use this data cleansing statistics. Then for configuration of model, this is what I was talking about. To form a model, you can use statistical hypothesis test. This is for ML model. You can still use hypothesis testing for model selection. We're going to see how we do it. We're going to discuss all four, how we do it. And then model prediction, estimation, statistics. So indirectly, we are using statistics in almost every step of data science and few steps of machine learning. Why am I not saying together? Because I said there can be purely a data science job, or there can be something which involves both data science and machine learning together. So let's start seeing. So in today's session, we'll be trying to cover these concepts on statistics, population and sample, central limit theorem, hypothesis testing. Then these different kinds of testing we have in hypothesis testing, point and interval estimations. Okay, point estimation and interval estimation. We'll try to cover these things. So let's see sample. Or maybe I can write population first. Population and sample. See, we were talking about ML data, if you remember. So this data is converted into system of linear equations, then into matrix. And then we have studied many techniques in matrices where we have identified the determinant, eigenvector, eigenvalue, decompositions, solving given system of linear equations we have been doing. Now, same way, you are given an ML data or general. I will not use the term ML because for understanding those system of linear equations, I said ML data, but you have a data set with you. Maybe this is the same SBI customers data, right? So population is nothing but the whole data which is given to us, the problem data, whatever we have. So suppose SBI has 1,000 customers, assume. Right. So the last 1 month transactions of these 1,000 customers. So full data, 1 month transactions of all those 1,000 customers can be considered as a population. It can be considered as a population. Okay. Now, what is a sample? Sample is just a small part of this randomly selected. So from this 1,000 customers, I have 1 month transaction of this 1,000 customers. From this, I would say maybe for 50 customers, one sample can be data of 50 customers of 1 month transactions. Right. So that can be a sample. Data set of 50 customers for all those 50 1 month transactions. This can be a sample. Or I can take for 100 customers 1 week transactions. So this also can be considered as a sample. Okay, right? I hope you understood population and sample. Population is the overall, the whole data set what we have with us, and sample is a small amount of data. Maybe it is just a little amount of information from that whole data set what we have with us, right? So SBI 1,000 customers, of 1 month transaction can be called as a population, and it is represented using P, and we have sample S. Right. Now, why do we have to study about population and sample? Let's see. So I said sample is just a small part. So if this is the population, this can be a sample. This can be a sample if this is population. So when you have huge data with you, lakhs of records of data you have with you cannot make any insights on that. Working with large data is difficult. Working with large data is difficult. So what we try to do here, we try to choose a random sample. Okay, you try to choose a random sample from that population. For that sample, you do your analysis. Whatever analysis you want to do, you do your analysis. After doing analysis for that small sample, you try to comment about the whole population. Let me give an example. I will say I have a statement here. This population P is the heights of students at NIT. Okay, heights of all the students. It may include BTech, different courses, MTech, PhD, or MCA, MSc. Lot of courses exist our end. So population is the heights of students of an entity. A sample can be heights of students of randomly chosen students. So I will be standing at the academic building or some classroom complex, and I will be randomly, all people are walking together. I am randomly stopping of some 100 students and finding their heights, which include students of all different courses. So randomly taking heights of the students. Now, why we need to study about population sample here is that, see, the question here is, what is the average height of students of NIT Trichy? What is the average height of students of NIT Trichy, irrespective of gender? Okay, that is the question. So, if I say the average height is 172 centimeters, for example, if I want to find it out, can I do it for whole students? We are having almost 8K to 9K students. We cannot find out the height of all the students, which is very difficult. So one way of doing it is randomly select few students, sample of out of 8,000 or 9,000 students, randomly select some 500 students or 200 students, calculate their height, find out their height, calculate their average. So the average height of randomly chosen 200 students is somewhere around 170 centimeters, you assume. Okay, so instead of calculating average height of the whole students, we are randomly picking up a sample, a small set of students. And for those small set of students, I am calculating the average. I get an average 170 centimeters. Using this sample information, we try to make comments on the population information. So we give statements about population, saying that the average heights of students of NIT Trichy, all students, can be somewhere near 170 centimeters. How you got this 170? By selecting only a small sample. So this may not be true. This is not exactly. If I really do, I may get 172, or maybe let me take 176. If I really calculate height of every student, but by choosing a small sample, I got 170. But it gives a rough idea. It gives an idea. So using these samples calculations or samples metrics, I will say, okay, I am trying to comment about the population's metric. I am saying the population, the heights of the whole population of NIT Trichy is 170, can be near 170. Right? So in data science, when you have huge data, we want to draw some insights. We cannot include that lakhs of data set or lakhs of records of information for doing business analysis. Instead, what we can do, we can randomly draw some samples. We can randomly draw some samples. Using those sample, you try to find out the insight, and you say that this is the same can be happening for the whole population. Okay, so SBI customers we are talking about. So when I take 50 customers transaction, maybe if I take 50 customers transactions, I found that 10K is going for shopping. Then around maybe some 5K for grocery. Like this, they will find out for 50 customers using their 1 month transaction. So based on this data, they may assume that, okay, this is the average value. So even those 1,000 customers might be spending 10K in their shopping. So they wanted to spoil us. They wanted to give some offer. They'll keep sending vouchers. They'll say, if you use our SBI card, debit or credit card in shopping, we are giving you 50%, 20%, 30%. What all offers they want to give, so that you keep using their banking facilities. So they want to draw some insights like this. So I hope you understood population and sample. So population is always represented as P and sample as small s. Population and sample. So in the whole data science, we'll be always playing with this samples data. We know about population as well, but we will be trying to find out insights using this samples data, and we'll try to comment about population data. Okay, so we will also see next one, that is central limit theorem. Central limit theorem. This is a very popular theorem in data science. Same thing. You will easily understand this. What we have already studied. Central limit theorem. It says that when you have a population P, of size capital N, okay, it means the number of elements, you can take number of students of NIT, anything. If the population size is N, you have a huge population of size N, then derive random samples. Derive random samples. Okay, so derive small samples S1, S2, S3, S4, and so on, Sn. So you derive random samples S1, S2, S3, S4, S5, so on, Sn. Okay, random samples you take. Sometimes you may get repeated elements here. You may get repeated elements. That's not the case. Understand the base case. So you randomly draw some samples. Suppose the question is to find out the mean of this population. Calculate the mean of this population, means average of the population. So there are some data points which I have. I want to find out what is the average of those data points. That is our task here. So what it says, it is very difficult to calculate mean of such huge data set. So randomly draw a sample of each of size m, n samples. Okay, now you find out mean for this small sample. Okay, let it be x1 bar. You find out mean for this sample S2. Okay, similarly you find out mean for all. You find out xn bar. What you have done, from the huge population, you are selecting small samples, S1, S2, so on, Sn. You have taken that. For each sample, you are calculating mean, average. So these are some numbers, maybe 20, 20, 30, 15, 14, 15, something, some numbers are there. You are randomly drawing a sample. For that sample, you are trying to find out average. X1 bar, X2 bar, X3 bar, so on. So what is this? These X1, X2 bars are called as, these are the means, right? These are the means of samples. These are the means of samples. Or I can say sample means. Sample means. Central limit theorem states that for this sample means, again you find out the mean. Again you find out the mean, x double bar. Okay, find out the mean, x double, means For this again, see, this x1 bar is also a number, right? This is a mean. This is also a small number. This is also a number. This is also a number. This is also a number. For these numbers, again you find out the mean. So this is mean of sample means. This x double bar is called as mean of sample means. Mean of sample means. Okay, mean of sample means. So central limit theorem states that for a given population P of size n, the mean of the population, which is represented as mu, the mean of the population mu is equal to mean of sample means, that is x double bar. This is your central limit theorem. Okay, so instead of calculating the mean, this is just an example. I'm talking about mean of small data, but it can be anything. Heights of student or marks of student, a lot of problems. We are going to explore them, right? So understand central limit theorem. When you have a population of size n, which is normally distributed, then you draw some random samples S1 to Sn. For each sample, you find out mean. Then for those sample means, again you find out a mean. That is called as mean of sample means. So the mean of population can be equal to the mean of sample means. This is your central limit theorem. Okay, to understand this once again with a small example, let me take some numerical example and explain you central limit theorem, very powerful theorem in statistics. You have a population, you have a population of 100 points, 100 students, you take anything. Okay, this is your population and capital N is 100. Now you derive some random samples, maybe 5, S1, S2, S3, S4, S5. Only 5 samples you derive. For maybe each of size 5. Each of size 5. So from this 100, I have taken some random 5, random 5, random 5 here and here. For these 5, you find out mean. Like this, you find out mean. Assume there are some numbers from 1 to 100. Assume there are some numbers from 1 to 100. So you have taken 5 each. Maybe this mean is 12. This is, since you've taken only 5, it is chance that you may get some 13, 27, or maybe 7 only, and here you got 20 or 31. These are 5 different means of 5 different samples. Now for these numbers, again find out average. Again you find out average. So this is around 100. Again, this can be somewhere around 20. Somewhere around 20. We got this. So with this, we can say the mean or the average of these 100 data points in this population can be equal to 20. Instead of calculating for whole 20, we are picking random samples, and for those samples, again, we are calculating mean. For those means, which is forming, see, this again looking like a sample. This again a sample. 12, 13 random points I have selected. For those samples, I am calculating mean. That is 20. So I am saying here that this mean of this population P can be equal to 20. I am saying can be equal to 20. That is your central limit theorem. I hope it is clear. So generally for population and sample, we try to calculate two things. One is mean, second one is variance. Here the number of data points is capital N. Here the number of data points is small n. So the mean for a population, sorry, we don't need this. The mean for this population with n elements can be simply 1 by capital N sigma xi, I equal to 1 to n or capital N. Normal, how you calculate mean. Here also it's same, 1 by small n sigma I equal to 1 to n xi. So sum of all the elements by n you do, you get sample mean, you get population mean. There is no difference. But for variance, it is here 1 by n sigma I equal to 1 to capital N xi minus mu whole square. This is your variance. This is your variance of population 1 by capital N, sigma equal to N, xi, that is 100 data points minus mu. Mu is the representation for population mean. Population mean. How do you represent sample mean? Sample mean can be represented as x bar. X bar. So here the variance in sample is 1 by n minus 1 sigma I equal to 1 to n xi minus x bar whole square. So these are the two equations for variance of population and sample. Okay, mean is again average of 100 elements or average of 5 elements that you can calculate easily. But for variance of those data points, it is 1 by capital N I equal 1 to n xi minus mu whole square. And here it is 1 by n minus 1 xi minus x bar whole square. Why are we using x bar here and mu for again for population and sample? P and small s, number of elements is n, here it is small n, mean it is mu, here it is x bar, standard deviation it is sigma, here it is variance is sigma square, here it is s square, sorry, here it is s square. Okay, so these are few representations we use in population and sample. So whole statistics runs behind these 6 parameters only. You can solve a lot of problems of data science by knowing these parameters. For some problem, these 3 are given, only one is given. For some problem, these 3 are given, only one is given. So a lot of problems exist. We will see that. So if we summarize again, central limit theorem, if you have a population P, which is normally distributed, then its mean can be equal to samples, mean of sample means, and its standard deviation can be equal to standard deviation of the samples by square root of n. This is your central limit theorem. Standard deviation of the variance of standard deviation, you take anything. I'm just ignoring this. I'm talking about variance. Standard deviation. See, variance means square. Standard deviation means this only. Okay. So sigma equal to s by square root of n. This is your central limit theorem. Right? To prove this, maybe we can take a small example of central limit theorem. Assume I have numbers 1, 2, 3, 4, 5. I have my population with 5 numbers 1 to 5. So n value is 5, mu value is also 5, I guess. Yes, no, it is 3. Average is 3, right? 5, 9, 12, 15 by 5, it is 3. Okay, so this is my mean and my total number. If I randomly take some maybe 3 samples, one sample S1 which contains 1, 2, 3. Let me take another sample 2, 3, 4, or another sample 3, 4, 5. I have taken 3 random samples, each of size 3. So this average here is 3 to 6 by 2, 2. This is 4, 7, 9 by 3, it is 3. And this is 9, 12 by 3, it is 4. Now these 3 again forms your number. So if you again find out mean of this 2 plus 3, 5 plus 4, 9 by 3, it is 3. So you see, when you randomly select some samples, 3 samples S1, S2, S3, for those samples you find out the mean. For those sample means, again if you find out the mean, it is 3, which is equal to your population mean. Maybe this is a small example. Even if you take larger one, you will not get exact. We are not saying that it is exactly equal to. So central limit theorem statement is like this: mu is equal to x bar, mean of sample means. So you have to, when you have lakhs of records, take some small samples of 20, 20 or 100, 100. For them, you find out the sample mean. For those means, you again find out another mean. So you can say that the population mean can be equal to the mean of sample means. Okay, this is your central limit theorem. Very powerful and very frequently asked questions in data science roles. Next, so we have covered about population, central limit theorem. Let's see hypothesis testing. Okay, very, very important concept, hypothesis testing. This is the core of statistics, which is used more than 90% in data science, hypothesis testing. So all these are under test under that. Okay, let's try to understand what is hypothesis testing. I'll first explain what is hypothesis. Hypothesis, any statement, any statement made against the population's data can be called as hypothesis. Any statement made on population's data can be called as hypothesis. Okay, so you will say the average placement package of my institute is 15 lakh. So that is the data. You are making a comment on the population's data of your institute. It is not about a particular branch, right? You are saying the average package for placements at our institute is 15 lakh. So that is about all the students of all the branches of different courses, BTech, MTech, PhD included together. So you are making a comment on the population's data. So such kind of statements made on the population's data are called as hypothesis. Okay. Now you have there are two types of hypothesis. There are two types of hypothesis. First one is null hypothesis, which is represented using H naught. Second one is alternate hypothesis, which is given as H1. Okay, null hypothesis and alternate hypothesis. There are two statements. What is null hypothesis? Okay, now see, you are making a statement, right? I am saying hypothesis is nothing but making a statement about population's data. You have that. What is null hypothesis? Whatever statement you made about the population's data, it is true until proven false. Null hypothesis is a statement made on the population's data and it is assumed to be true until it is proven as false. That is your null hypothesis. Okay, until proven as false. That is null hypothesis. I hope you understood. Hypothesis means making a comment. Whatever comment you made, assuming it is true. So, null hypothesis means any statement made on population's data is assumed to be true until it is proven false. What is alternate hypothesis? It is just opposite to null hypothesis. It is just opposite to null hypothesis. So, if you say that the average salary of students of NIT Trichy is 15 lakh, I am saying is 15 lakh. I am saying alternate hypothesis says that it is not equal to 15 lakh. It is not equal to 15 lakh, right? So this is about hypothesis. Now, but in alternate hypothesis, we can have multiple cases. In alternate hypothesis, we can have multiple cases. So let us again discuss with an example. So H naught says that the average amount of Coke filled in the bottles by Coca-Cola company, the average amount of Coke filled by the company in plastic bottles, okay, is exactly 500 ml in a 500 ml bottle. This is your H naught. Company says the average amount of Coke filled in the bottles by our company is exactly equal to 500 ml. What will be H1? H1 will be it is not equal to 500. It is not equal to 500. But there are two other cases also. Yes, this is one case. We can say that it is not equal to 500, but sometimes also we can prove that H1 is less than 500 ml or the amount, or it is greater than 500 ml. So there are three cases altogether. Null hypothesis says it is equal to. Alternate hypothesis says it is not equal to. Along with that, there are two more cases that it can be greater than or it can be less than. So when you are proving it is not equal to, when you are proving it is not equal to 500 ml, If you go a little deeper, you can make a comment like this, that it is greater than 500 or it is less than 500, right? In alternate hypothesis. So the lot of statistical problems are there where some data is given to us, some information is shared to us. Based on that, we will try to make a comment that whether it is yes really equal to or not equal to. So this in alternate hypothesis having two problems. One, proving that it is not equal to. So when the company make a statement, there can be a lot of people working on this statement. So one kind of people can prove, they can somehow prove that no, it is not equal to 500. I don't know whether it is greater than or less than, but it's definitely not equal to. That is one kind of a proof we can do, or somebody else can work and say, no, it is less than 500, or somebody can say it is greater than 500. Okay, hypothesis testing, null hypothesis, and alternate hypothesis, right? So these two are different in hypothesis testing. What is hypothesis testing? So I said you right. We have studied about population and sample. We say that we use samples data to make a comment about population data, right? We have population, we have a small sample. We use the samples information and we make comments about the population, right? So in hypothesis testing, we have two different kinds of testing. Why we use this testing? When somebody is making a comment like this, whether it is true or false. Okay, so your hypothesis testing is example again. I will take the heights of the students at NIT Trichy. H naught is H naught is high average height. Average height is equal to 172 centimeters at NIT. Okay, and my H1 will be, I want to say the average height is not equal to 172 centimeters. So how you derive that? You have taken a samples data, but you from the samples data, you are saying that the average height is 172. This is not from the population. This is not from the population's data. It is from the samples data. And I am making a claim on population. That's what I said. Any statement made on the population's data based on the statistics samples data can be called as a hypothesis. So this is such kind of a statement. H naught is a null hypothesis. It's a statement made on the population. What is the statement made? The average height of students at NIT is 172 centimeters. How I make this statement? Using samples data. What will be my alternate hypothesis? It says that it is not equal to 172. Okay. Now, when I made a statement like this, I have to test it whether really the claim made. I am a faculty here at NIT. I made a claim. Okay. So I am making a claim that the average height of the students of NIT is 172 centimeters based on the samples data. Based on the samples data. So you want to disprove me. You want to prove me that no, it is wrong or right. So in that case, you have to use hypothesis testing techniques to prove that the statements made on some populations like this are valid or invalid. For that, we use hypothesis testing techniques. I'll repeat once again what we are trying to say. You have a population, you have a sample. We cannot play with large data. We always comment using the samples data. Okay, you always comment using the samples data about the population. Now, what is hypothesis testing? So, H naught is that the amount of the Coke is 500 ml. Company is saying H1, I am saying it is not equal to 500 ml. So, when company made a statement that it is equal to 500, I want to test this. I want to test this statement H naught, whether what he has said is right or wrong. Then I can prove. It means, if you observe now, it means either of this can be true. After doing some hypothesis testing techniques, after applying some testing techniques, either H naught can be true or H1 can be true. So maybe he is true or maybe I am true that it is not equal to 500. Right? So which one is true among these two? That can be done using hypothesis testing techniques. There are some testing techniques which will help us to make some validations whether what that fellow is telling is right or wrong. Okay, so at any point of time, either this can be true or this can be true. Right. Now let's see about hypothesis testing. Hypothesis testing. There are two types of testing in this: parametric, non-parametric. What are these parametric testing and non-parametric testing? I hope you understood about hypothesis testing. We use hypothesis testing techniques to validate whether the statements given by somebody has done research. They have found something. You want to validate it, whether it is true or false. For validation, we are using it. Parametric testing technique means, in hypothesis testing, parametric means if the metrics, if the information about population and sample are given, means they say out of total 100 students in my class, the average marks is 70. They will say total students in my class is 100, the average marks is 70. They told. So this is given as the information. So he is making a claim that for 100 students, the average is 70. As a teacher, I am making a claim that it is 70. You want to prove it, whether it is, you want to test it, whether it is really 70 or not. So informations in parametric testing technique, informations like about n, mu, x bar, small n, this all are given. If some of these values are given, these are all the parameters. Parameters of what? They are the parameters of sample or population. So in a given problem, if some information related to these parameters is given, then we apply some certain kinds of tests. We have different testing techniques. And if none of these are given, we apply some certain kinds of testing techniques. Okay, parametric testing, non-parametric testing. In parametric testing, the parameters of population or sample are given. In non-parametric, no information is given. Only some data is given to us. They have not talked about mean. They are not talking about number of. They are not talking about number of elements in the population, number of elements in the sample. Then only if they give some data, then it is non-parametric testing. Right? So let's see what is our parametric testing. What are the different types here? So in parametric testing, again we have multiple testing techniques: T test, Z test, and F test. T test, Z test, and F test. In non-parametric, we have one test, that is chi-square test. So it is represent something like this: chi-square test. So total we have four different kinds of hypothesis testing. Three are parametric, one is non-parametric. It means here they don't give the information. Maybe I will tell an example here. I'll just quickly make you understand what is the difference between parametric and non-parametric. They give some information like this. Maybe gender. Yes, let's take a gender. So male, female, pet animal, dog, cat. Okay, something like this: male, female, dog, cat. I have a small data set where men, number of people who are male, they like dogs more, so that is around 250 count, whereas cats is just 150, and female dogs is 50, and this is around 200. So they have given some data like this. Maybe in some small village, we did survey, we find out that male number of males or gents who like dogs is 250 and who likes cat is 150. Number of females who like dog is 50 as their pet animal, and number of females who like cat as their pet animal is 200. Now the question is, can you make a comment? Can you draw an insight? Is there any relation between gender and the animal? Is it that all males are liking dogs and all females are liking cats? So your H naught will be, your H naught null hypothesis will be, yes, there is a relation between male gender and animal. It is there is some trend can be observed from that. It is from the data. It is observed that male are liking only dogs and females are liking only cats. That is your H naught. But is it really true or not? We have to identify that. This is some random data. Maybe if I put 150 here, you cannot make some judgment here with that. Okay, by seeing numbers, you cannot comment. This is a simple example I'm giving. But if you assume large one, if you assume larger one, we cannot say that no, there is some relation between the gender and the maybe best can be understood by this example. I don't know whether I can talk this, but already we have completed elections. So we have gender, we have male and female, we have some party A, political party B and C. Okay, so 100, 180, maybe 75, 120, 96, maybe some 113. Some data is like this. Okay, so is there any gender preference for political parties? These three are political parties ABC. Okay, so we have to make an insight. We want to draw an insight, identify a pattern. Is it more that females are always voting to party C? Then party C can bring new kind of in their manifesto. They can include new things only for female, because it is observed from the data that females are voting more to party C. So the question here is to find out, is there any relationship between the gender and the political party? We are making some insights. This is a small data, but in data science, in real time, they have to make some big insights. They have to, from the big data, large data, they have to draw some insights. So for that, we use this non-parametric test. I hope you understood the relation between parametric and non-parametric. Here, they have not given anything about total number of voters in that village, total number of political party in that village, total number of male, female, nothing is given to us. Some random data is given. You draw the insight. H naught is H naught, null hypothesis. H naught is, yes, there is relationship between gender and political party. H1 is not, there is no relationship. You prove, you do some steps and prove that really whether there is a relationship or not. For solving such kind of problems, we use non-parametric test. Whereas parametric test, we are given data something like this. See, for this dog cat only, I will tell you, population, there exists a population of 200 people in the village, and it is observed sample data. This is population count. Okay, so the average number of people who are using dogs as their pet animals is 30. Average number of people who are using dogs as their pet animals is 30, and who are using cat is around 70. So they are giving some numbers. They are giving some means to us. Mean, capital N. They are giving some information to us. Okay. So using this numerical data, you can apply P, Z and F test. Where if there is no such numerical data, some sample data is given, then you go and apply this non-parametric test, that is chi-square test. Okay. I hope you got a little idea about hypothesis testing techniques. We have parametric and non-parametric. In parametric, we have T test, Z test, and F test. Here we have chi-square test. So using this, we'll try to prove whether H0 or H1 is true. And in statistics, it is believed that, see, suppose you this is H1 is about equal to 500 ml, for example. H1 H0 H1 is about not equal to 500 ml. This is the problem we are trying to solve. What is this 500 ml? Coca-Cola company says the average amount of Coke which I am filling in our bottles is exactly 500. There is not even 0.001% mistake. H1, I want to prove that no, there is some difference. That is not equal to. You apply some test, any of these tests you apply. Okay, after applying these testing techniques, you will find out the result. So either this can be true or this can be true. But solution always has to be given in terms of H naught. Like this. H naught is accepted. This is a standard in statistics. H naught is accepted. If you prove using these testing techniques that the whatever statement made by the company is true, then you have to write your answer as H naught is accepted. If you prove that using some testing techniques that no, it is not equal to, you have to say H naught is rejected. You will not say H1 is accepted. You will say H naught is rejected, because H naught is the very powerful statement. Only that can be proved or disproved, right? H naught is accepted or H naught is rejected. So hypothesis testing techniques, right? So